What if I told you there are worlds in our solar system so far away that it takes light over 4 hours just to reach them, and so cold that temperatures drop to 224 derg, making them more frozen than anything you can imagine on Earth? These are our ice giants, Uranus and Neptune, sitting at mind-blowing distances of 2.9 billion and 4.5 billion kilometers from the Sun, respectively. Uranus is so cold it holds the record for the coldest atmospheric temperature ever measured in our solar system, while Neptune experiences supersonic winds that could destroy anything in their path. If you want to explore more incredible cosmic mysteries and discover the most extreme places in our universe, subscribe to the Lazy Cosmos and hit that notification bell, because we're about to journey to some of the most isolated and frozen worlds you've ever heard of. When we truly grasp the distances to Uranus and Neptune, our understanding of scale in the solar system completely transforms. Uranus sits at an average distance of 2.9 billion kilometers from the Sun, while Neptune lurks even farther at 4.5 billion kilometers away. These numbers sound abstract until we realize what they actually mean for the reality of these worlds. To put this in perspective, if you could somehow drive a car at highway speeds directly to these planets without stopping, it would take you over 3,300 years to reach Uranus and more than 5,100 years to reach Neptune. The light from our Sun, traveling at the fastest speed possible in the universe, takes 2 hours and 40 minutes to reach Uranus and over 4 hours to reach Neptune, compared to just 8 minutes and 20 seconds to reach Earth. The isolation of these ice giants becomes even more striking when we consider their orbital periods. Neptune takes 165 Earth years to complete a single orbit around the Sun, meaning that since its discovery in 1846, it has only completed one full orbit in 2011. Uranus takes 84 years for each orbit, and due to its unique sideways rotation, each of its poles experiences 42 years of continuous sunlight, followed by 42 years of total darkness. Imagine living through seasons that last longer than entire human lifetimes, where winter doesn't just mean a few cold months, but decades of perpetual night. The vast distances also create incredible communication challenges that make these worlds almost unreachable by conventional means. When NASA's Voyager 2 spacecraft flew by these planets in the 1980s, it took over 4 hours for any signal to travel between Earth and the spacecraft when it reached Neptune. This means that if something went wrong during the crucial flyby moments, mission control on Earth would only learn about it 4 hours after it happened, and any corrective commands would take another 4 hours to reach the spacecraft. By that time, the brief encounter would be long over, making real-time control impossible and requiring the spacecraft to operate with complete autonomy during the most critical moments of the mission. These distances also explain why these worlds remained largely mysterious until very recently. While ancient civilizations could see Mercury, Venus, Mars, Jupiter, and Saturn with the naked eye, Uranus wasn't discovered until 1781 by William Herschel, and Neptune wasn't found until 1846. Even with powerful telescopes, these planets appear as tiny, distant points of light, revealing few details about their true nature. The fact that we know anything about them at all is a testament to the incredible precision and ingenuity of space exploration technology. The journey to these distant worlds represents one of the greatest challenges in space exploration. Current chemical rockets would take 10 to 12 years just to reach Uranus, and even longer to reach Neptune, requiring perfect planetary alignments that occur only once every 175 years. The Voyager 2 mission took advantage of such a rare alignment in the late 1970s, using the gravitational pull of Jupiter and Saturn to slingshot itself toward the outer planets. Without this cosmic coincidence, the mission would have been impossible with the technology available at the time. Temperature extremes beyond imagination. The cold at Uranus and Neptune defies earthly comparison, creating conditions so extreme that they challenge our understanding of what constitutes a habitable environment. Uranus holds the record for the coldest atmospheric temperature ever measured in our solar system, with readings dropping to an incredible 224 degrees Celsius, or 307 degrees. To understand how extreme this is, consider that this temperature is only 49 degrees above absolute zero, the theoretical point where all molecular motion stops. At these temperatures, the very air we breathe on Earth would not just freeze, but would form solid blocks harder than steel. The atmospheric composition of these worlds creates their own unique temperature signatures. Both planets have atmospheres dominated by hydrogen and helium, with Uranus consisting of about 83% hydrogen, 15% helium, and 2% methane, while Neptune has similar proportions. The methane in their upper atmospheres absorbs red light from the already weak sunlight that reaches them, giving both planets their characteristic blue color, while contributing to their frigid temperatures. However, the small amount of methane present means that unlike Earth's greenhouse effect, these atmospheres provide no warming whatsoever. What makes Neptune particularly fascinating is that despite being much farther from the Sun than Uranus, it's actually slightly warmer, with atmospheric temperatures around 218 degrees Celsius compared to Uranus's record-breaking 224 degrees Celsius. This seemingly impossible situation occurs because Neptune generates its own internal heat through radioactive decay and gravitational compression from its formation billions of years ago. Neptune radiates about 2.6 times more energy than it receives from the Sun, creating a mysterious internal heat source that scientists are still working to understand. Uranus, mysteriously, shows no evidence of generating significant internal heat, making it the coldest of all planets, despite not being the most distant from the Sun. The temperature structure of these planets creates complex atmospheric layers that would be completely alien to anyone familiar with Earth's weather patterns. In the troposphere of both planets, temperatures actually increase with depth due to the immense pressure and residual heat from formation. At the base of Uranus's atmosphere, temperatures can reach 320 K, or 47 degrees Celsius, warmer than a comfortable room on Earth. Yet this heat is trapped under such enormous pressure and distance that it never reaches the surface we observe. These temperature gradients create convection currents and weather patterns unlike anything seen on inner planets. The extreme cold has profound effects on the chemical behavior of these atmospheres. Elements and compounds that exist as gases on Earth become liquids or solids at these temperatures. Water, which covers most of Earth's surface as a liquid, would be rock-hard ice on these worlds. Carbon dioxide, which we exhale as a gas, would be frozen solid. Even more exotic processes occur at these temperatures. Scientists theorize that the extreme conditions deep within these planets could create diamond rain, where carbon compounds are compressed and frozen into actual diamonds that fall through the atmosphere like hailstones. The temperature differences between day and night on these worlds are also extreme in ways that Earth dwellers cannot imagine. While Earth's atmosphere and oceans help distribute heat around the planet, creating relatively moderate temperature differences between day and night, the thin atmospheres and extreme distances of Uranus and Neptune mean that any area not receiving direct sunlight becomes incredibly cold incredibly quickly. During Uranus's 42-year winter periods, temperatures drop even further, creating conditions that would instantly freeze any Earth-based life form solid. Perhaps most remarkably, these extreme temperatures exist in dynamic, active atmospheres. Despite the incredible cold, both planets experience weather patterns and atmospheric dynamics. Neptune hosts some of the fastest winds in the solar system, reaching speeds of up to 2,100 kilometers per hour, nearly twice the speed of sound on Earth. These supersonic winds occur in an atmosphere so cold that most Earth substances would be solid, demonstrating that extreme cold doesn't necessarily mean inactive or static conditions. The implications of these temperature extremes extend far beyond simple comfort concerns. They represent fundamental barriers to exploration and understanding. Any spacecraft visiting these worlds must be designed to operate in conditions where most materials become brittle and electronics fail. The extreme cold also affects how we observe these planets from Earth. Their thermal radiation is so weak that detecting heat signatures requires the most sensitive instruments available to astronomy. Yet despite these challenges, these frozen worlds continue to reveal secrets about planetary formation, atmospheric dynamics, and the extreme conditions possible in our solar system, reminding us that the universe contains environments far more extreme and alien than anything we experience on our temperate home planet. Deep within the icy giants of Uranus and Neptune lies one of the most perplexing mysteries in planetary science: their bizarre and chaotic magnetic fields that defy everything we understand about how planets should behave. Unlike Earth, Jupiter, and Saturn, which all possess orderly dipolar magnetic fields resembling giant bar magnets with clear north and south poles, Uranus and Neptune present us with magnetic environments so twisted and jumbled that they seem to follow no recognizable pattern whatsoever. The magnetic field of Uranus is tilted an incredible 59 degrees from its rotation axis, while Neptune's magnetic field is offset by 47 degrees compared to Earth's relatively modest 11-degree offset. These aren't just minor variations. They represent fundamental differences in how these planets generate and maintain their magnetic environments, creating conditions that would be utterly alien to any spacecraft attempting to navigate through their magnetospheres. The strength of these chaotic magnetic fields is equally remarkable and unsettling. Neptune's magnetic field is 27 times more powerful than Earth's, while Uranus exhibits a magnetic field that varies dramatically in strength, sometimes reaching 4 times Earth's power, and at other times dropping to nearly half our planet's magnetic intensity. This variability creates an electromagnetic environment of constant flux and unpredictability, where charged particles from the solar wind interact with the planetary magnetic fields in ways that create aurora displays and radiation patterns unlike anything seen elsewhere in our solar system. The magnetic field lines don't flow in the neat, organized patterns we observe around Earth, but instead loop in and out in shifting patches that change configuration as the planets rotate, creating a magnetic maze that would challenge any understanding of planetary physics. Recent breakthrough research has finally begun to unravel the mystery behind these bizarre magnetic behaviors, and the explanation is more exotic than anyone initially imagined. The secret lies deep within the planet's interiors, where the familiar substances of water, methane, and ammonia exist under such extreme pressure and temperature that they behave in ways completely foreign to our earthly experience. Under the crushing pressures found deep within these ice giants, millions of times greater than Earth's atmospheric pressure, these planetary ices undergo a process called phase separation, where they naturally separate into distinct layers, much like oil and water refuse to mix. The upper layer, rich in water, experiences convection currents that generate electrical conductivity and magnetic fields, while the deeper layers containing carbon and nitrogen compounds remain relatively stable and don't contribute significantly to magnetic field generation. This creates a situation where the magnetic field is generated only in a thin outer shell of the planet, rather than throughout a large, solid core-like Earth experiences. Without a massive solid core to stabilize and organize these magnetic field lines, they become tangled and chaotic within the liquid layers, creating the jumbled electromagnetic environments that Voyager 2 discovered during its historic flybys in the 1980s. What makes this discovery even more fascinating is the role of exotic forms of ice that exist nowhere on Earth. Under the extreme conditions within these planets, water can form crystalline structures where hydrogen atoms move freely throughout the lattice, creating what scientists call hot ice, a form of ice that conducts electricity despite being solid. These conductive ice forms can reach temperatures of thousands of degrees while maintaining their crystalline structure under the immense pressures, creating electrical pathways that contribute to the chaotic magnetic field generation. The hydrogen atoms in these exotic ice forms carry electrical charges throughout the crystal lattice, essentially turning portions of the planet's interiors into massive, chaotic electrical generators. The atmospheric dynamics created by these magnetic field interactions produce some of the most violent weather patterns in our solar system. Neptune experiences winds that reach speeds of 2,100 kilometers per hour, nearly twice the speed of sound on Earth, driven by the complex interactions between its internal heat generation, chaotic magnetic field, and the minimal solar energy it receives at such vast distances from the Sun. These supersonic winds occur in an atmosphere where temperatures hover around 218 degrees Celsius, creating conditions where most substances would be frozen solid, yet dynamic atmospheric processes continue to rage with incredible violence. The magnetic field, interactions with charged particles in the atmosphere, create aurora displays that would be spectacular beyond imagination, with electromagnetic phenomena occurring across the entire planet rather than being confined to polar regions like Earth's aurora. Uranus presents an even more complex case due to its unique 98-degree axial tilt, which means it essentially rotates on its side. This extreme tilt, combined with its chaotic magnetic field, creates a magnetosphere that tumbles through space like a spinning corkscrew, presenting different magnetic orientations to the solar wind as the planet rotates every 17 hours. During parts of its 84-year orbit, Uranus's magnetic poles point directly toward or away from the Sun, creating what scientists call a polon configuration that occurs nowhere else in our solar system. This creates periods where the planet's magnetosphere is either fully exposed to or completely shielded from the solar wind, resulting in dramatically different electromagnetic environments that change not just seasonally, but throughout each Uranian day. The magnetic field chaos of these planets creates practical challenges for any future exploration missions that extend far beyond simple navigation difficulties. Spacecraft electronics must be shielded against magnetic field variations that can fluctuate wildly and unpredictably, and communication systems must account for electromagnetic interference that can disrupt signals in ways that don't occur around planets with orderly magnetic fields. The charged particle environments around these planets create radiation belts and electromagnetic phenomena that could damage sensitive scientific instruments or interfere with data collection, requiring entirely new approaches to spacecraft design and mission planning. Perhaps most remarkably, these chaotic magnetic environments may actually provide clues about thousands of similar ice giant planets that exist throughout our galaxy. Recent exoplanet discoveries suggest that ice giants like Uranus and Neptune may be among the most common types of planets in the universe, meaning that understanding their magnetic field generation could help us predict the electromagnetic environments of countless worlds orbiting other stars. The phase separation processes that create these chaotic magnetic fields likely occur in any planet with sufficient mass and the right combination of ices, suggesting that the bizarre magnetic environments of our ice giants may actually represent the norm rather than the exception in planetary electromagnetics. The ongoing mystery of these magnetic fields continues to challenge our understanding of planetary formation and evolution. The fact that these chaotic electromagnetic environments have persisted for billions of years suggests that the internal processes generating them are stable and long-lasting, even though their surface manifestations appear random and unpredictable. This stability within chaos represents a fundamental aspect of how large planetary systems can maintain complex electromagnetic environments over geological timescales, providing insights into the long-term evolution of planetary magnetospheres and their effects on atmospheric retention and space weather patterns. As we continue to study these distant ice giants, their magnetic field mysteries remind us that the universe contains electromagnetic environments far more complex and alien than anything we experience in our Earth-centric understanding of how planets should behave. Orbiting through the frigid darkness that surrounds Uranus and Neptune, a collection of mysterious moons drifts in eternal winter, each one presenting its own unique story of survival in the harsh environment at the edge of our solar system. These lunar companions, numbering 29 around Uranus and 16 around Neptune, exist in conditions so extreme that they challenge our understanding of what constitutes a dynamic celestial body. Yet recent discoveries reveal that even in this frozen realm, geological activity and complex processes continue to unfold across timescales that span millions of years. The moons of these ice giants represent some of the most alien and fascinating objects in our solar system, where water exists as rock-hard ice, where nitrogen geysers erupt into space, and where gravitational forces create internal heating in worlds that should be completely frozen solid. Neptune's moon system tells one of the most dramatic stories of planetary violence and reconstruction in our solar system's history. The entire system is dominated by Triton, a massive moon that makes up nearly all of the total mass of Neptune's satellite system, with all other moons together comprising only 1/3 of 1% of the total lunar mass around the planet. This extreme imbalance occurred because Triton wasn't born around Neptune. It was violently captured from the distant Kuiper belt, likely as part of a binary system that was torn apart during a chaotic gravitational encounter billions of years ago. When Triton was captured, its highly eccentric orbit caused catastrophic perturbations throughout Neptune's original moon system, causing the existing moons to collide and grind themselves into rubble that eventually reaccreted into the smaller moons we observe today. Triton itself represents one of the most geologically active bodies in the outer solar system, despite existing at temperatures of 235 degrees, where nitrogen behaves like water does on Earth. During Voyager 2's flyby in 1989, the spacecraft detected active nitrogen geysers erupting from Triton's surface, shooting plumes of dark material up to 8 kilometers high into the moon's thin atmosphere. These geysers occur because Triton has a retrograde orbit, meaning it orbits Neptune backwards compared to the planet's rotation, creating tidal heating that generates enough internal energy to drive geological activity even in the extreme cold of the outer solar system. The surface of Triton is composed primarily of nitrogen ice, with traces of methane and carbon monoxide, creating a landscape that would appear almost mirror-like under the weak sunlight that reaches Neptune's distance from the Sun. The smaller moons of Neptune tell equally fascinating stories of survival and destruction in the chaotic environment created by Triton's capture. Recent discoveries of 3 new moons around Neptune, including S2021N1 and S2002N5, reveal orbital groupings that suggest these small bodies are fragments of larger parent moons that were shattered by ancient collisions with comets or asteroids. These moon fragments follow similar orbital paths, indicating they were once part of larger bodies that broke apart, leaving behind a collection of rubble pile moons that orbit in families through the outer reaches of Neptune's gravitational influence. The discovery of these fragment families provides direct evidence that the early solar system was far more chaotic and violent than previously understood, with frequent collisions occurring between various objects throughout the outer planetary regions. Uranus presents an equally complex moon system, with 29 confirmed satellites ranging from massive, geologically diverse worlds to tiny captured asteroids that represent the smallest moons ever detected around any planet. The 5 major moons of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, each tell unique stories of geological evolution in the extreme cold and isolation of the Uranian system. These medium-sized moons, composed primarily of ice and rock, with significant amounts of ammonia, methane, and water ice, present several puzzles that challenge our understanding of how moons evolve in the outer solar system. Ariel and Umbriel are nearly identical in size and density, yet Ariel shows clear evidence of recent volcanic and tectonic activity with young surface features, while Umbriel presents a heavily cratered, ancient surface that appears geologically dead and unchanged for billions of years. Miranda, the smallest of Uranus's major moons, may be the most geologically bizarre object in our entire solar system. When Voyager 2 flew past Miranda during its 1986 encounter with Uranus, it revealed a surface unlike anything seen elsewhere, featuring a chaotic mixture of old, heavily cratered terrain alongside young geological features, including canyons up to 20 kilometers deep, deeper than the Grand Canyon and nearly 3 times the height of Mount Everest. The cliffs and fault systems on Miranda's surface suggest that this small moon, only 470 kilometers in diameter, has somehow generated enough internal heat through tidal interactions to completely resurface portions of itself multiple times throughout its history, creating a patchwork landscape that appears to have been assembled from different geological eras. The newly discovered moon around Uranus, designated S2023 U1, represents the cutting edge of our ability to detect extremely small objects in the outer solar system. At only 8 kilometers in diameter, this tiny world is likely the smallest moon in the Uranian system, taking 680 days to complete each orbit around its parent planet. The discovery of such a small object using ground-based telescopes required special image processing techniques and represents a technological achievement that pushes the boundaries of astronomical observation. This new moon follows a similar orbital path to other outer Uranian satellites like Caliban and Stefano, suggesting it may be part of a collision family created when a larger parent body was shattered by an impact event millions of years ago. The extreme cold at the distances of Uranus and Neptune creates unique conditions on these moons that don't exist anywhere else in the solar system. Water ice becomes harder than granite at these temperatures, while substances like methane and nitrogen that exist as gases on Earth form solid landscapes and geological features. On Triton, nitrogen ice flows like glaciers do on Earth, creating smooth plains and complex terrain features through processes that operate on geological timescales. The weak sunlight that reaches these distant moons provides so little energy that any geological activity must come from internal heat sources such as radioactive decay or tidal heating, making active moons like Triton extremely rare and scientifically precious. The orbital dynamics of these moon systems create complex gravitational interactions that continue to reshape the satellite populations over millions of years. Many of the smaller moons exist in unstable orbits that will eventually lead to their destruction, either through collision with their parent planet or by being torn apart by tidal forces. The Portia group of small moons around Uranus, consisting of 8 tiny satellites, including Bianca, Cressida, and Desdemona, all follow slowly decaying orbits that will eventually cause them to either break apart into ring material or crash into Uranus itself over the next few million years. These ongoing orbital evolution processes mean that the moon systems we observe today around Uranus and Neptune are temporary configurations that will look completely different in the distant future. Future exploration of these distant moon systems presents extraordinary challenges and opportunities. The extreme distances mean that any spacecraft mission to study these moons in detail would require decades of travel time and represent some of the most technically demanding space missions ever attempted. However, the potential scientific rewards are enormous, as these moons preserve records of conditions in the early outer solar system and may harbor unique environments where exotic forms of geological activity continue despite the extreme cold and isolation. The discovery of active processes on worlds like Triton suggests that even the most distant and apparently lifeless corners of our solar system may contain dynamic environments that could teach us about the possibilities for geological activity throughout the galaxy. These frozen moons, existing in the perpetual winter at the edge of our solar system, remind us that even in the most extreme environments, the forces of nature continue to shape and reshape worlds in ways that challenge our earthbound understanding of what constitutes an active, evolving planetary body. The story of humanity's encounter with Uranus and Neptune represents one of the most extraordinary achievements in space exploration history, accomplished by a single spacecraft during a journey that would span over a decade and cover more than 4 billion kilometers through the cold darkness of the outer solar system. Voyager 2, launched in August 1977, was originally designed for a 4-year mission to study Jupiter and Saturn. But through careful planning and a rare celestial alignment that occurs only once every 175 years. Mission scientists were able to extend its journey to include flybys of both ice giants, making it the first and still the only spacecraft from Earth to visit these distant worlds. The spacecraft's encounter with these frozen giants would revolutionize our understanding of the outer solar system and reveal that even the most distant corners of our cosmic neighborhood harbor active, dynamic environments that challenge every assumption we had made about planetary science. The journey to Uranus required Voyager 2 to travel for 4.5 years after leaving Saturn, during which time the spacecraft operated in complete autonomy while traveling through a region of space so remote that radio signals took over 2.5 hours to reach Earth. As the spacecraft approached Uranus in late 1985, scientists on Earth faced the unprecedented challenge of exploring a world about which virtually nothing was known beyond its basic orbital characteristics and the fact that it rotated on its side. The lighting conditions at Uranus were 400 times dimmer than those on Earth, requiring Voyager 2's cameras and instruments to operate at the absolute limits of their sensitivity to capture any meaningful data during the brief encounter window. The flyby itself lasted only 5.5 hours, during which time the spacecraft had to autonomously execute a complex sequence of observations while traveling at over 15 kilometers per second relative to Uranus, leaving no room for real-time corrections or adjustments from mission control on Earth. What Voyager 2 discovered during its Uranus encounter completely transformed our understanding of planetary science and revealed a world far more complex and dynamic than anyone had imagined. The spacecraft discovered 10 new moons, doubling the known satellite population of Uranus and revealing a complex system of small bodies with names drawn from Shakespeare's works: Puck, Portia, Juliet, Cressida, Rosalind, Belinda, Desdemona, Cordelia, Ophelia, and Bianca. These moons, most smaller than 100 kilometers in diameter, orbit within Uranus's ring system and play crucial roles in shepherding and maintaining the planet's narrow rings through gravitational interactions. The rings themselves prove to be unlike anything seen elsewhere in the solar system, consisting of dark particles that reflect only a few percent of the sunlight that reaches them, making them nearly invisible, except when viewed edge-on or backlit by the sun. The magnetic field of Uranus, revealed by Voyager 2, presented one of the most shocking discoveries of the entire mission. Unlike every other planet with a known magnetic field, Uranus's magnetosphere was tilted 55 degrees away from its rotation axis and offset from the planet's center, creating a chaotic electromagnetic environment that tumbles through space as the planet rotates every 17 hours. This bizarre magnetic field configuration suggested that the generation of planetary magnetism operated through fundamentally different processes within ice giants compared to terrestrial planets or gas giants, launching decades of theoretical work to understand how such unusual magnetic fields could form and persist over geological timescales. Recent analysis of the Voyager 2 data has revealed that the spacecraft's encounter with Uranus occurred during extraordinarily rare conditions that may have fundamentally skewed our understanding of the planet. New research published in Nature Astronomy shows that Voyager 2 observed Uranus during a period of intense solar wind activity that compressed the planet's magnetosphere to less than half its normal size, creating conditions that occur less than 5% of the time. The solar wind dynamic pressure during the flyby was approximately 20 times higher than normal, squashing Uranus's protective magnetic bubble from its typical extent of about 28 planetary radii down to only 17 radii. This extreme compression likely explains many of the anomalous observations that have puzzled scientists for decades, including the unusually intense radiation belts and the apparent absence of plasma that made Uranus's magnetosphere appear almost completely empty compared to other planets. The implications of this discovery are staggering, as it means that our entire scientific understanding of Uranus has been based on observations made during conditions so extreme that they represent less than 1 week out of every 4 years of the planet's behavior. If Voyager 2 had arrived just a week earlier, when the solar wind was 20 times weaker, scientists would have encountered a completely different magnetosphere with a fundamentally different structure and composition. The radiation belts that appeared so mysteriously intense during the flyby were likely temporary features created by the extreme compression, while the vacuum magnetosphere that seemed devoid of plasma was probably a transient state caused by the unusual solar wind conditions stripping particles from the magnetic field lines. Voyager 2's subsequent encounter with Neptune in August 1989 proved even more dramatic and scientifically rewarding as the spacecraft approached to within 4,800 kilometers of the planet's cloud tops during the closest flyby of its entire 12-year planetary tour. The Neptune encounter revealed a world of extraordinary dynamic activity, with the Great Dark Spot, a storm system larger than Earth, raging in the planet's atmosphere alongside winds reaching speeds of 100 kilometers per hour, the fastest recorded in the solar system. The spacecraft discovered 6 new moons around Neptune, including Proteus, which at 400 kilometers across is the largest irregularly shaped moon in the solar system, as well as 4 new rings that appeared as faint arcs from Earth-based observations, but were revealed to be complete ring systems with complex internal structure. The crown jewel of the Neptune encounter was the detailed study of Triton, Neptune's largest moon, which Voyager 2 revealed to be one of the most geologically active bodies in the outer solar system, despite surface temperatures of 235 degrees C. The spacecraft detected active nitrogen geysers erupting from Triton's surface, shooting dark material up to 8 kilometers high into the moon's thin atmosphere, proving that geological activity could persist even in the extreme cold and isolation of the outer solar system. Triton's surface displayed a bizarre cantaloupe terrain in its southern hemisphere, with complex patterns of ridges and depressions that suggested ongoing geological processes driven by tidal heating from its retrograde orbit around Neptune. The technical achievement represented by Voyager 2's ice giant encounters cannot be overstated, as the spacecraft had to operate flawlessly for over a decade in the harsh environment of deep space while traveling billions of kilometers from Earth. By the time Voyager 2 reached Neptune, its radio signals took over 4 hours to reach Earth, meaning that any malfunction during the critical flyby period would be discovered only hours after it occurred, with any corrective commands taking another 4 hours to reach the spacecraft. The fact that Voyager 2 successfully completed both encounters while collecting thousands of images and vast amounts of scientific data represents one of the pinnacles of human technological achievement and space exploration capability. The legacy of Voyager 2's encounters with Uranus and Neptune extends far beyond the immediate scientific discoveries, as these flybys demonstrated that robotic exploration could successfully reach and study the most distant worlds in our solar system. The mission proved that complex, long-duration space missions could operate reliably for over a decade while traveling through regions of space where solar power is inadequate and communication delays make real-time control impossible. The discoveries made during these brief encounters, from active geology on Triton to the complex ring systems of both planets to the bizarre magnetic field configurations, continue to influence planetary science today and provide the foundation for all proposed future missions to the ice giants. Perhaps most importantly, the Voyager 2 encounters revealed that even the most distant and apparently frozen worlds in our solar system harbor complex, active environments that continue to evolve and change over geological timescales. The nitrogen geysers of Triton, the dynamic atmospheres of both ice giants, and the ongoing evolution of their moon systems demonstrate that the outer solar system is not a static, frozen wasteland, but rather a region where fundamental physical processes continue to shape and reshape worlds in ways that we are only beginning to understand. These discoveries have transformed our perspective on planetary habitability and the potential for active environments throughout the galaxy, showing that distance from a star does not necessarily preclude geological activity and complex environmental dynamics. When Voyager 2's cameras first captured detailed images of Neptune on August 25, 1989, they revealed a world wrapped in teal and cobalt-colored cloud bands, punctuated by the most extraordinary atmospheric feature ever discovered in the outer solar system: the Great Dark Spot, a massive anticyclonic storm larger than Earth itself, raging with winds that reach speeds of 2,100 kilometers per hour. This colossal tempest, comparable in size to Jupiter's famous Great Red Spot, represented just one component of Neptune's incredibly dynamic atmospheric system, which scientists discovered operates with a violence and complexity that defies everything we thought we knew about planetary weather in the cold, distant reaches of our solar system. The storm's dark coloration came not from the storm itself, but from a window in Neptune's high-altitude methane cloud deck that allowed observers to peer deeper into the planet's atmosphere, revealing the churning dynamics occurring in the layers beneath the visible cloud tops. The atmospheric discoveries made during Voyager 2's flyby completely revolutionized our understanding of how weather systems can operate in the extreme conditions of the outer solar system. Despite receiving only 3% of the sunlight that Jupiter receives, Neptune's atmosphere proved to be far more dynamic and energetic than the gas giants, with wind speeds reaching up to 3 times those found on Jupiter and 9 times stronger than the most powerful hurricanes ever recorded on Earth. Most remarkably, these supersonic winds blow primarily westward, in the opposite direction to the planet's rotation, creating a retrograde atmospheric circulation pattern that occurs nowhere else in our solar system and challenges fundamental theories about how planetary atmospheres should behave under the influence of a world's rotational dynamics. The complexity of Neptune's atmospheric structure became apparent as Voyager 2's instruments revealed multiple distinct cloud decks operating at different altitudes and exhibiting completely independent behavior patterns. The spacecraft discovered that cloud systems could emerge and dissolve within a matter of hours, while giant storms circled the entire planet in just 16 to 18 hours in the upper atmospheric layers. These rapid changes indicated an energy source far more powerful than solar heating alone, suggesting that Neptune's atmospheric dynamics are driven primarily by internal heat generation rather than external solar input, making it fundamentally different from the weather systems we observe on Earth or even on Jupiter and Saturn. Alongside the Great Dark Spot, Voyager 2 discovered several other remarkable atmospheric features that demonstrated the incredible complexity of Neptune's weather systems. An almond-shaped feature designated D2 appeared as a smaller dark spot with its own complex circulation patterns, while a bright, fast-moving cloud formation, dubbed Scooter, raced around the planet at speeds that exceeded even the rapid circulation of the larger storm systems. The methane clouds in Neptune's upper atmosphere cast visible shadows on the layers below, creating a three-dimensional atmospheric structure where weather patterns operated simultaneously at multiple altitudes, each layer influencing and being influenced by the dynamics occurring above and below it. The discovery of lightning within Neptune's atmosphere added another layer of complexity to the planet's already extraordinary weather systems. Voyager 2's planetary radio astronomy experiment detected approximately 60 lightning flashes during the encounter, with each discharge releasing energies exceeding 700 million joules, far more powerful than typical lightning strikes on Earth. These Neptunian electrostatic discharges occurred within the planet's ammonia cloud layers and generated electromagnetic waves detectable across a frequency range from 50 Hz to 12 kHz, indicating electrical activity of unprecedented intensity occurring within the frozen atmospheric layers of this distant world. The plasma wave detections made during Voyager 2's closest approach provided the first measurements of Neptune's atmospheric electrical activity, with the spacecraft's instrumentation recording plasma densities ranging from 10^3 to 10^1 particles per cubic centimeter. These measurements revealed that Neptune's atmosphere maintains a complex ionosphere despite its extreme distance from the Sun, with charged particles interacting in ways that generate aurora displays far weaker than those seen on Earth or other planets, but still detectable by Voyager 2's sensitive instruments. The auroral activity occurs within Neptune's tilted and offset magnetic field, creating electromagnetic phenomena that shift and change as the planet rotates every 16 hours and 6.7 minutes. Perhaps most remarkably, subsequent observations by the Hubble Space Telescope revealed that the Great Dark Spot had completely disappeared by 1994, just 5 years after Voyager 2's discovery. This vanishing act demonstrated that Neptune's atmospheric features are far more transient than similar storms on other giant planets, suggesting that the planet's weather systems operate on timescales of years rather than centuries or millennia. The disappearance of such a massive storm system indicates that Neptune's atmosphere contains energy sources and circulation patterns capable of both creating and destroying Earth-sized weather features within remarkably short periods, making it one of the most dynamic atmospheric environments in the entire solar system. The methane content of Neptune's atmosphere, comprising about 1% of the total atmospheric composition, plays a crucial role in both the planet's distinctive blue coloration and its complex weather patterns. Methane molecules in the upper atmosphere preferentially absorb red wavelengths of sunlight while reflecting blue light back to space, giving Neptune its characteristic azure appearance. However, the methane also participates in complex photochemical reactions driven by the weak ultraviolet radiation that reaches Neptune's distance from the Sun, creating hydrocarbon compounds that form haze layers and contribute to the complex multi-layered cloud structure observed throughout the planet's atmosphere. The wind patterns discovered on Neptune revealed circulation systems operating under physical conditions that shouldn't theoretically support such dynamic activity. The supersonic winds occur in atmospheric layers where temperatures drop to 218 degrees Celsius, conditions so cold that most substances would be frozen solid. Yet the atmosphere maintains fluid dynamics that create circulation patterns more violent than anything observed on planets receiving hundreds of times more solar energy. The westward flowing winds reach their maximum speeds in the planet's southern hemisphere, where they achieve velocities that approach the speed of sound in Neptune's atmosphere, creating sonic booms and shock waves that propagate through the atmospheric layers. The energy source driving Neptune's extraordinary atmospheric activity remains one of the most compelling mysteries in planetary science. The planet radiates approximately 2.6 times more energy than it receives from the Sun, indicating a powerful internal heat source that could be maintained by radioactive decay within the planet's core. Gravitational compression from the planet's formation process, or exotic phase transitions occurring within the high-pressure interior layers. This internal energy generation provides the driving force for the supersonic winds, the rapidly evolving storm systems, and the complex multi-layered atmospheric structure that makes Neptune's weather patterns so dramatically different from those of any other planet in our solar system. The atmospheric pressure and density variations throughout Neptune's atmospheric layers create conditions where different weather phenomena can occur simultaneously at various altitudes. The upper atmospheric layers, where methane clouds form and the fastest winds occur, operate under pressures similar to Earth's stratosphere, while deeper layers experience crushing pressures that compress atmospheric gases into liquid and eventually solid phases. This creates a vertical atmospheric structure where weather patterns transition from gas phase dynamics in the upper layers to liquid phase convection in the deeper regions, generating a complexity of atmospheric behavior that challenges our understanding of how planetary weather systems can operate under such extreme conditions. The legacy of Neptune's atmospheric discoveries continues to influence planetary science today, as scientists use the insights gained from Voyager 2's observations to understand similar atmospheric dynamics on exoplanets throughout the galaxy. The discovery that such dynamic weather systems can operate in the cold, distant regions of a solar system has expanded our understanding of where active atmospheric processes might occur on planets orbiting other stars, particularly those in the outer regions of their planetary systems, where traditional models would predict only static, frozen environments. Neptune's violent weather systems demonstrate that internal energy sources can drive complex atmospheric dynamics regardless of stellar heating, opening up possibilities for active atmospheric environments on countless worlds throughout the universe that were previously considered too cold and distant to support dynamic weather patterns. When Voyager 2 approached the ice giants, one of the most surprising discoveries awaiting the spacecraft was the existence of complete ring systems around both Uranus and Neptune. Intricate collections of particles and debris that had remained largely invisible to Earth-based telescopes due to their extreme faintness and the vast distances involved. The rings of Uranus had been discovered accidentally in 1977 during a stellar occultation event, when astronomers noticed that starlight dimmed briefly as the star passed behind what they initially thought was empty space around the planet, revealing the presence of narrow, dark rings, unlike anything seen around Saturn. These Uranian rings proved to be among the darkest objects in the solar system, reflecting only about 2% of the sunlight that strikes them, making them essentially invisible except when viewed edge-on, or when they block background starlight during occultations. The ring system of Uranus consists of 13 distinct rings, with the main rings designated by Greek letters Alpha, Beta, Gamma, delta, and epsilon, representing some of the narrowest and most precisely confined ring structures known in planetary science. The epsilon ring, the outermost and most massive of Uranus's rings, varies in width from 20 to 100 kilometers as it orbits the planet, demonstrating a complex elliptical structure that defies simple explanations of how ring particles should behave under gravitational influence. What makes these rings particularly mysterious is their incredible narrowness compared to their orbital distances. They maintain sharp edges and precise boundaries, despite being composed of countless individual particles that should theoretically spread out over time through gravitational interactions and collisions. Voyager 2's close-up examination of the Uranian ring system revealed that the particles composing these rings are primarily boulder-sized chunks of rock and ice, significantly larger than the mostly centimeter-sized particles that make up Saturn's bright rings. The dark coloration of Uranus's ring particles suggests they are composed of organic compounds that have been radiation processed over millions of years, creating a charcoal-like surface that absorbs rather than reflects sunlight. This organic material may originate from the methane-rich environment of the Uranian system, where methane molecules are broken down by ultraviolet radiation and charged particles to form complex hydrocarbon compounds that coat the ring particles in a dark, sooty residue. The discovery that two small moons, Cordelia and Ophelia, orbit just inside and outside the epsilon ring provided the first direct evidence of shepherd moons, small satellites whose gravitational influence confines ring particles within narrow bands. These shepherd moons, each only about 40 kilometers in diameter, exert gravitational forces that prevent the ring particles from spreading outward or spiraling inward toward Uranus, maintaining the ring structure over geological timescales. The precise orbital dynamics required for this shepherding process demonstrate the incredible complexity of gravitational interactions that can occur within planetary ring systems, where tiny perturbations can have dramatic effects on the long-term stability of particle orbits. Neptune's ring system presented even greater mysteries when Voyager 2 discovered that what appeared from Earth to be incomplete ring arcs were actually complete rings with dramatic variations in particle density. The Adam's ring, Neptune's outermost ring, exhibits three bright arc segments with poetic names, Liberté, Égalité, and Fraternité, that contain significantly more material than the rest of the ring, creating the illusion of incomplete rings when viewed from Earth-based telescopes. These bright arcs are maintained by gravitational resonances with Neptune's moon Galatea, which orbits inside the ring and creates a 42-43 orbital resonance that concentrates particles into specific locations along the ring's orbit. The four complete rings of Neptune, Gale, Leverrier, Lassell, and Adams, each exhibit different characteristics that reflect the complex history of the Neptunian system. The innermost Gale ring is extremely faint and broad, spanning a width of about 2,000 kilometers, but containing very little material, while the Leverrier ring is narrow and relatively dense, similar to some of the main rings of Uranus. The Lassell ring is actually a plateau of material rather than a distinct ring, extending from the Leverrier ring outward to the Adams ring and representing a more diffuse distribution of particles throughout this region of Neptune's environment. The composition and structure of Neptune's rings reveal clues about the violent history of the planet's moon system. The ring particles are dark and reddish in color, similar to the surface materials found on Neptune's small inner moons, suggesting that the rings may be composed of debris from collisions that occurred when these moons were repeatedly struck by comets or asteroids over billions of years. The fact that Neptune's rings are so faint and contain relatively little material compared to other planetary ring systems indicates that they are probably young features, perhaps only a few 100 million years old, and are continuously being replenished by ongoing collisional processes involving the planet's small moons. Voyager 2's detailed analysis of both ring systems revealed that ring particles in the outer solar system behave very differently from those around the inner planets. At the extreme distances of Uranus and Neptune, where temperatures drop below 200 degrees C, water ice becomes harder than granite, while other materials undergo phase transitions that dramatically affect their physical properties. The low temperatures also mean that particle collisions occur at much lower velocities, allowing ring particles to stick together more easily when they collide, potentially leading to the formation of larger bodies within the rings over geological timescales. The gravitational environment around ice giants creates unique conditions for ring dynamics that don't occur around other types of planets. The relatively low mass of Uranus and Neptune compared to Jupiter and Saturn means that their ring systems extend much closer to the planet's surface relative to the planet's radius, creating stronger tidal forces that can disrupt small moons and prevent the accretion of ring particles into larger bodies. These tidal forces also create complex resonance patterns with the planet's moons, leading to gaps, density waves, and other structures within the rings that reflect the gravitational influence of nearby satellites. The discovery of ring systems around both ice giants fundamentally changed our understanding of how common ring systems are throughout the solar system and the galaxy. Prior to Voyager 2's discoveries, rings were thought to be relatively rare features associated primarily with Saturn, but the ice giant encounters revealed that ring formation may be a natural consequence of having a system of small moons in a region where tidal forces can disrupt solid bodies. This suggests that ring systems may be common features around giant planets throughout the galaxy, particularly around ice giants that may represent the most numerous type of large planet in the universe based on recent exoplanet discoveries. The long-term evolution of the ice giant ring systems presents fascinating questions about planetary dynamics over geological timescales. Computer simulations suggest that the current ring systems around both Uranus and Neptune are probably temporary features that will either spiral into the planets or be disrupted and dispersed within 10 to 100 million years unless they are continuously replenished by ongoing collisional processes. This means that the ring systems observed by Voyager 2 represent snapshots of dynamic processes that have been operating throughout the history of these planetary systems, with rings forming, evolving, and disappearing as moons are disrupted by impacts and tidal forces reshape the distribution of debris around each planet. The study of ice giant ring systems has also provided insights into the early history of our solar system, when similar collisional processes may have been much more common throughout all planetary environments. The relatively pristine state of the Uranian and Neptunian systems, which have experienced fewer major perturbations than the inner solar system planets, may preserve evidence of the types of processes that shaped all planetary ring systems during the early epochs of solar system formation, Understanding how these ring systems form, evolve, and eventually disperse helps scientists model similar processes that may have occurred around Earth and other planets billions of years ago, when the solar system was young and collisional events were far more frequent than they are today. Perhaps most remarkably, the ice giant ring discoveries demonstrated that even in the cold, distant regions of our solar system, dynamic processes continue to reshape planetary environments over millions of years. The ongoing evolution of these ring systems, driven by the complex interplay of gravitational forces, collisional processes, and orbital dynamics, shows that the outer solar system is not a static frozen wasteland, but rather an active environment where planetary systems continue to evolve and change. These discoveries have expanded our understanding of where dynamic planetary processes can occur and have implications for understanding similar processes around the countless ice giant exoplanets that appear to be common throughout our galaxy. When Voyager 2 approached the ice giants, its magnetometer instruments detected some of the most bizarre and unexpected electromagnetic environments ever encountered in our solar system, revealing magnetic field configurations so unusual that they challenge fundamental theories about how planetary magnetism should work. The magnetic fields of both Uranus and Neptune proved to be dramatically different from the orderly dipolar magnetic fields found around Earth, Jupiter, and Saturn, instead presenting chaotic, twisted electromagnetic environments that seem to follow no recognizable pattern or organization. These discoveries would fundamentally reshape our understanding of planetary magnetism and demonstrate that the universe contains electromagnetic phenomena far more complex and alien than anything we had previously imagined possible within planetary systems. The magnetic field of Uranus, as measured by Voyager 2 during its 1986 flyby, presented an immediate puzzle that has continued to challenge planetary scientists for nearly 4 decades. Unlike Earth's magnetic field, which is tilted only 11 degrees from the planet's rotational axis, Uranus exhibits a magnetic field tilted an incredible 59 degrees away from its rotation axis, creating a magnetosphere that tumbles through space like a spinning corkscrew as the planet rotates every 17 hours and 14 minutes. Even more remarkably, the center of this magnetic field is offset from the planet's physical center by approximately 1/3 of Uranus's radius, meaning that the magnetic field appears to be generated not from the planet's core, but from a region displaced significantly toward the planet's surface layers. Recent, groundbreaking analysis of the original Voyager 2 data has revealed that the spacecraft encountered Uranus during extraordinarily unusual conditions that may have fundamentally skewed our understanding of the planet's normal electromagnetic environment. The research shows that Voyager 2 observed Uranus's magnetosphere in an anomalously compressed state, with the magnetopause, the boundary between the planet's magnetic field and the solar wind, located at only 17 Uranian radii from the planet's center instead of the typical 22 radii expected under normal solar wind conditions. This compression occurred because the spacecraft arrived during a period of intense solar wind activity, with dynamic pressure approximately 20 times higher than average, creating conditions that occur less than 5% of the time throughout Uranus's orbit around the Sun. The implications of this discovery are staggering, as it means that virtually everything we thought we knew about Uranus's magnetic environment was based on observations made during conditions so extreme they represent less than 1 week out of every 4 years of the planet's normal behavior. If Voyager 2 had arrived just 1 week earlier, when the solar wind pressure was 20 times weaker, the magnetosphere would have extended to approximately 28 Uranian radii, presenting a completely different electromagnetic environment with fundamentally different plasma populations, radiation belt characteristics, and magnetic field line configurations. The vacuum magnetosphere that appeared mysteriously empty of plasma during Voyager 2's flyby was likely a temporary condition created by the extreme solar wind compression, while the unusually intense electron radiation belts were probably enhanced by the magnetospheric compression process. Neptune's magnetic field measurements revealed an equally complex and puzzling electromagnetic environment that defied conventional understanding of planetary magnetism. The planet's magnetic field is tilted 47 degrees from its rotational axis and offset from Neptune's center by 0.55 planetary radii, more than half the planet's radius, creating an electromagnetic environment even more chaotic than that found at Uranus. The field strength varies dramatically across Neptune's surface, reaching 1.42 microteslas at the equator, while exhibiting complex quadrupole and octupole components that create a magnetic field structure resembling multiple bar magnets oriented at various angles to each other rather than a single, organized dipolar field. Voyager 2's magnetometer measurements during its 38-hour passage through Neptune's magnetosphere revealed radiation belts containing trapped protons, electrons, and ionized molecular hydrogen and helium, but with charged particle densities significantly lower than those found at Uranus. The spacecraft's approach trajectory allowed it to enter Neptune's magnetosphere through what scientists call a pole-on configuration, where the magnetic field lines were oriented directly toward the approaching spacecraft, providing a unique sampling opportunity of the planet's magnetic cusp region, an area where solar wind particles can directly enter the magnetosphere along magnetic field lines. The chaotic nature of both ice giant magnetic fields creates electromagnetic environments that vary dramatically as the planets rotate, causing the magnetic field orientation to change continuously with respect to the incoming solar wind. This rotation-induced variability means that the magnetospheric boundaries, radiation belt configurations, and plasma populations around both planets undergo regular cycles of compression and expansion every few hours as different portions of their tilted, offset magnetic fields face the solar wind. These rapid changes create dynamic electromagnetic environments unlike anything found around other planets in our solar system, where the magnetic fields remain relatively stable and predictable. The discovery of these bizarre magnetic field configurations led to revolutionary theories about how planetary magnetism can be generated within ice giant interiors. Unlike the iron cores that generate magnetic fields in terrestrial planets, or the metallic hydrogen layers responsible for magnetism in gas giants, the ice giants appear to generate their magnetic fields through entirely different processes occurring within their unique internal structures. Recent computer modeling suggests that the magnetic fields originate from electrical currents flowing within thin layers of supersonic water ice, where hydrogen atoms can move freely through the crystal lattice while oxygen atoms remain fixed, creating a conductive medium that can sustain electrical currents and generate magnetic fields. These supersonic ice layers exist under the extreme pressure and temperature conditions found within ice giant interiors, where pressures exceed millions of times Earth's atmospheric pressure and temperatures reach thousands of degrees despite the planet's frozen external appearances. The phase separation processes that occur under these conditions create distinct layers with different electrical properties, allowing magnetic field generation to occur in narrow shells rather than throughout large, solid cores like those found in other planets. This shell-based magnetic field generation explains both the offset nature of the fields and their complex, non-dipolar structure, as the generating regions are relatively small and located away from the planetary centers. Voyager 2's measurements also revealed that the magnetic field strengths of both ice giants vary significantly with location and time, creating electromagnetic environments that pulse and fluctuate as the planets rotate. The spacecraft's magnetometer detected magnetic field variations that correlated with the planet's rotation periods, indicating that the field generation mechanisms are closely tied to the internal structure and rotation of the ice giant interiors. These variations create complex patterns of magnetic field line reconnection, plasma acceleration, and particle precipitation that generate aurora displays far different from those seen on Earth or other planets. The radiation environments around both ice giants proved to be far more complex than initially expected, with Voyager 2 detecting multiple distinct radiation belt regions around each planet. These radiation belts contain energetic particles trapped by the chaotic magnetic fields, but their structure and behavior differ dramatically from the relatively stable radiation belts found around planets with dipolar magnetic fields. The particles in ice giant radiation belts follow irregular, unpredictable trajectories as they bounce between magnetic mirror points that shift location as the planets rotate, creating radiation environments that pose significant challenges for any future spacecraft missions. The electromagnetic discoveries made by Voyager 2 have profound implications for understanding similar processes throughout the galaxy, as ice giants appear to be among the most common types of large planets based on recent exoplanet surveys. The unique magnetic field generation mechanisms operating within these worlds may represent the standard electromagnetic environment for countless ice giant exoplanets orbiting other stars, suggesting that chaotic, non-dipolar magnetic fields may be far more common in the universe than the orderly dipolar fields we observe around Earth and the gas giants in our solar system. Perhaps most remarkably, the ice giant magnetic field discoveries demonstrate that planetary electromagnetic environments can be far more diverse and complex than previously imagined. The fact that two planets of similar size and composition can generate such dramatically different magnetic field configurations, both utterly unlike anything found elsewhere in our solar system, suggests that planetary magnetism represents a far more diverse phenomenon than our Earth-centered perspective had led us to believe. These discoveries continue to challenge our understanding of how electromagnetic fields can be generated and maintained within planetary bodies, opening up possibilities for even more exotic magnetic environments around the countless worlds that exist throughout the cosmos. The ongoing analysis of Voyager 2's magnetic field data, combined with new theoretical models of ice giant interiors, continues to reveal new insights into these mysterious electromagnetic environments nearly 4 decades after the original encounters. Advanced computer simulations can now model the complex phase transitions and electrical processes occurring within ice giant interiors, providing new explanations for the chaotic magnetic fields and their unusual orientations. These studies suggest that the ice giant magnetic fields represent stable, long-term configurations that have persisted for billions of years despite their chaotic appearance, indicating that complex electromagnetic environments can be maintained over geological timescales, even when they appear random and unpredictable from external observations. Among all the celestial bodies encountered during Voyager 2's epic journey through the outer solar system, perhaps none presented a more perplexing and fascinating mystery than Miranda, the innermost of Uranus's 5 major moons. When the spacecraft approached to within 28,260 kilometers of this small, icy world on January 24, 1986, the images that emerged revealed a surface so bizarre and geologically impossible that scientists initially questioned whether they were looking at a single coherent body or the fragments of multiple worlds somehow held together by gravity. Miranda's landscape defied every conventional understanding of how small moons should behave, presenting a chaotic mixture of ancient, heavily cratered terrain alongside remarkably young geological features that appeared to have formed within the last few million years. An impossibility for a world that should have been geologically dead for billions of years. The most striking features of Miranda are the massive coronae, huge oval-shaped regions surrounded by concentric ridges and grooves that stretch across hundreds of kilometers of the moon's surface. These coronae, named Arden, Elsinore, and Inverness after locations in Shakespeare's plays, represent some of the most dramatic topographical variations found anywhere in the solar system. With elevation changes exceeding 20 kilometers from the deepest valleys to the highest ridges. The largest of these features, Arden Corona, spans over 300 kilometers across and contains fault systems so deep and complex that they dwarf Earth's Grand Canyon, creating a landscape that appears to have been turned inside out through some unknown geological process that generated enormous amounts of internal heat within this tiny 470-kilometer diameter world. The fault systems crisscrossing Miranda's surface tell a story of repeated episodes of intense geological activity that should have been impossible given the moon's small size and distance from any significant heat source. Verona Rupes, a massive cliff face discovered in Voyager 2's images, rises approximately 20 kilometers above the surrounding terrain, making it one of the highest cliff faces known in the solar system and nearly 3 times taller than Mount Everest. The formation of such dramatic topographical features requires enormous amounts of energy to fracture and reshape solid rock and ice. Yet Miranda orbits so far from the Sun that solar heating provides virtually no energy, and the Moon is too small to retain significant heat from its formation billions of years ago. The surface composition of Miranda, as revealed through spectroscopic analysis of Voyager 2's data, consists primarily of water ice mixed with rocky material and small amounts of organic compounds that give some regions a darker coloration. However, the distribution of these materials across the Moon's surface follows no logical pattern, with bright, relatively pure ice regions adjacent to dark, heavily processed terrains that appear to have undergone extensive space weathering and radiation processing. This mixture of surface compositions suggests that Miranda has experienced repeated episodes of geological activity that have brought subsurface materials to the surface through volcanism, tectonism, or impact processes that should not occur on such a small, distant world. The mystery deepens when considering Miranda's orbital characteristics and their relationship to the other Uranian moons. Miranda orbits Uranus every 1.4 Earth days in a nearly circular orbit that places it within the planet's intense radiation environment, where energetic particles constantly bombard the Moon's surface. However, computer models of orbital evolution suggest that Miranda should have achieved a stable, tidally locked orbit billions of years ago, meaning that tidal heating from gravitational interactions with Uranus should have ceased long before the geological features we observe could have formed. The presence of such recent geological activity therefore requires an explanation that goes beyond simple tidal heating mechanisms. Recent theoretical work has proposed that Miranda may have undergone a catastrophic breakup and reassembly process sometime in its geological history, which could explain the bizarre mixture of terrain types and geological features observed on its surface. This hypothesis suggests that a massive impact event completely shattered the Moon into fragments that subsequently reaccreted under their own gravity, creating a jumbled reassembly of different types of material and geological terrains. Such a breakup and reassembly event could generate the internal heating necessary to drive the geological processes that created the coronae, fault systems, and other dramatic surface features, while also explaining why different regions of the Moon appear to have completely different geological histories. Beyond Miranda, Voyager 2's encounters with the other major moons of Uranus revealed a diverse collection of worlds, each with their own unique characteristics and evolutionary histories. Titania, the largest of the Uranian moons at 1,378 kilometers in diameter, displays a surface marked by enormous fault systems and canyon networks that indicate significant geological activity sometime in its past. The Messina Chasmata, a system of interconnected canyons on Titania's surface, stretches for over 1,500 kilometers across the Moon's southern hemisphere and reaches depths of several kilometers, representing one of the largest canyon systems known on any moon in the solar system. The formation of these canyon systems requires internal processes that could fracture and reshape the Moon's icy crust over geological timescales, suggesting that even relatively large moons in the outer solar system can maintain geological activity far longer than previously thought possible. Ariel, despite being significantly smaller than Titania, at only 1,158 kilometers in diameter, surprisingly displays the youngest and most geologically active surface among all the Uranian moons. The Moon's surface is covered with extensive valley systems, fault scarps, and what appear to be flows of icy material that have resurfaced large portions of the Moon within the last few 100 million years. The brightness and relatively pristine appearance of Ariel's surface indicate that active geological processes have been operating recently enough to erase most impact craters, suggesting ongoing internal heating mechanisms that continue to drive geological activity despite the Moon's small size and great distance from the Sun. The source of this internal heating remains mysterious, as Ariel's orbit is not sufficiently eccentric to generate significant tidal heating from interactions with Uranus. In stark contrast to Ariel's youthful appearance, Umbriel presents one of the darkest and most heavily cratered surfaces found anywhere in the Uranian system. This 169-kilometer diameter moon appears to have remained geologically inactive for billions of years, with an ancient surface that preserves impact craters from the early bombardment period of solar system formation. The dark coloration of Umbriel's surface may result from the accumulation of organic compounds created by radiation processing of methane and other hydrocarbons in the Uranian system, creating a layer of dark, carbonaceous material that coats the Moon's icy surface. Despite being similar in size to Ariel, Umbriel shows no evidence of recent geological activity, highlighting the complex factors that determine whether small moons can maintain active geology over geological timescales. Oberon, the outermost of Uranus's major moons at a diameter of 1,523 kilometers, presents a surface intermediate between the youthful appearance of Ariel and the ancient terrain of Umbriel. The Moon displays numerous large impact craters alongside evidence of limited geological activity, including what appear to be dark deposits within some crater floors that may represent cryovolcanic materials erupted from the Moon's interior. The presence of these dark deposits suggests that Oberon may have experienced episodic periods of geological activity throughout its history, with internal heating processes occasionally becoming active enough to drive volcanic eruptions of water and other materials to the surface. The small moons discovered by Voyager 2 within the Uranian system present their own collection of mysteries and surprises. These 10 newly discovered satellites, ranging in size from about 40 to 160 kilometers in diameter, follow orbits that place them within Uranus's ring system, where they play crucial roles in shepherding ring particles and maintaining the structure of the narrow rings through gravitational interactions. Puck, the largest of these small moons at about 160 kilometers across, displays a heavily cratered surface with a distinctive dark coloration that may result from the accumulation of ring particle material or organic compounds processed by radiation within the Uranian magnetosphere. The discovery that several of these small moons follow orbital resonances with each other and with the ring systems suggests complex gravitational interactions that have shaped the evolution of the entire Uranian satellite system over geological timescales. These orbital resonances can amplify small perturbations in the Moon's orbits, leading to orbital instabilities that may eventually result in collisions or the disruption of some of these small bodies. Computer simulations indicate that the current configuration of small moons within the Uranian system is probably temporary, with several of these bodies following slowly decaying orbits that will lead to their destruction within the next few million years. Recent reanalysis of Voyager 2's data has revealed that the spacecraft's encounter with the Uranian system occurred during highly unusual space weather conditions that may have significantly affected the observations of both the planet and its moons. The discovery that an intense solar wind event compressed Uranus's magnetosphere just days before Voyager 2's flyby suggests that many of the anomalous readings and apparently inactive conditions observed around the Uranian moons may not represent their normal state. Under typical conditions, the moons may be actively releasing gases and particles into the magnetosphere through geological processes such as cryovolcanism or sublimation, creating a more dynamic and potentially habitable environment than previously thought. This realization has profound implications for understanding the potential for geological activity and even habitability within the Uranian moon system. If the moons are indeed more active than Voyager 2's observations suggested, they may harbor subsurface oceans or active geological processes that could create environments suitable for life. The presence of internal heating mechanisms capable of maintaining liquid water beneath the icy surfaces of these moons would place them among the potentially habitable environments in our solar system, despite their extreme distance from the Sun and the frigid conditions that prevail throughout the Uranian system. When Voyager 2 completed its remarkable 12-year journey through the outer solar system with its closest approach to Neptune on August 25, 1989, The spacecraft's cameras captured images of a moon that would fundamentally challenge our understanding of where life might exist in the universe. Triton, Neptune's largest satellite, revealed itself to be one of the most geologically active and potentially habitable worlds in our solar system. Despite existing in conditions so cold that nitrogen, a gas at Earth's temperatures, behaves like water on this distant, frozen moon. The discovery of active nitrogen geysers erupting from Triton's surface into the thin atmosphere represented one of the most shocking revelations of the entire Voyager program, proving that geological activity could persist in the extreme cold and isolation of the outer solar system, billions of kilometers from the warming influence of the Sun. Triton's surface, as revealed through Voyager 2's high-resolution imaging, presents a landscape unlike anything found elsewhere in our solar system. The southern hemisphere displays what scientists have dubbed cantaloupe terrain, a bizarre pattern of oval-shaped depressions and ridges that create a texture resembling the skin of a cantaloupe melon, formed through processes that remain largely mysterious even decades after their discovery. These unusual surface features, ranging from a few kilometers to several dozen kilometers across, appear to result from some form of internal geological process that has reshaped Triton's icy crust repeatedly over geological timescales, creating a complex pattern of ridges and valleys that indicates ongoing tectonic activity beneath the frozen surface. The active nitrogen geysers observed by Voyager 2 demonstrated that Triton maintains sufficient internal heat to drive volcanic processes, despite surface temperatures that plunge to 235 degrees, cold enough to freeze nitrogen solid. The spacecraft detected at least 8 active geyser systems erupting from Triton's surface, shooting columns of dark material up to 8 kilometers high into the moon's tenuous atmosphere before being carried downwind by atmospheric circulation patterns. These geysers appear to be seasonal phenomena, becoming more active when Triton's south pole is tilted toward the sun during Neptune's southern summer, suggesting that even the minimal solar heating at Neptune's distance can trigger geological processes when combined with internal heat sources. The composition of these nitrogen geysers provides crucial insights into the subsurface environment beneath Triton's frozen crust. Spectroscopic analysis of the erupted material reveals a complex mixture of nitrogen, methane, and organic compounds that have been processed through chemical reactions occurring within Triton's interior. The presence of these organic materials suggests that Triton's subsurface environment contains the chemical building blocks necessary for life, including carbon-based compounds that could serve as nutrients for potential biological processes. The fact that these materials are being actively transported from the interior to the surface through volcanic processes indicates that Triton maintains a dynamic chemical cycle that could potentially support life forms adapted to extremely cold conditions. The mechanism driving Triton's geological activity stems from its unique orbital characteristics and the complex gravitational interactions with Neptune. Triton follows a retrograde orbit around Neptune, meaning it orbits in the opposite direction to the planet's rotation, a configuration that occurs nowhere else among the major moons in our solar system. This retrograde motion creates continuous tidal heating as Triton's orbit slowly decays toward Neptune, generating the internal energy necessary to maintain liquid regions beneath the frozen surface and drive the geological processes that create the geysers and surface features we observe today. Computer models of Triton's internal structure suggest that beneath its frozen nitrogen and water ice crust lies a subsurface ocean of liquid water mixed with ammonia, a natural antifreeze that allows liquid water to exist at temperatures far below its normal freezing point. This subsurface ocean may be tens of kilometers deep and could contain more liquid water than exists in all of Earth's oceans combined, making it one of the largest reservoirs of liquid water in the solar system. The presence of this hidden ocean, combined with the active geological processes that transport materials between the interior and surface, creates conditions that could potentially support microbial life forms adapted to high-pressure, low-temperature environments. The recent reanalysis of Voyager 2's data from the Uranus system has revealed that the Uranian moons may also harbor similar subsurface oceans and active geological processes. The discovery that Voyager 2 encountered Uranus during extremely rare space weather conditions suggests that the apparently inactive state of the Uranian moons observed during the flyby may not represent their normal condition. Under typical circumstances, these moons may be actively releasing gases and other materials into the magnetosphere through geological processes similar to those observed on Triton, indicating that they too may maintain subsurface liquid environments capable of supporting life. This revelation has profound implications for astrobiology and the search for life in our solar system. If the moons of Uranus do indeed harbor subsurface oceans and active geology, it would mean that potentially habitable environments exist throughout the outer solar system, far beyond the traditional habitable zone where liquid water can exist on a planet's surface. The presence of multiple ocean worlds in the outer solar system would dramatically expand the number of potential habitats for life and suggest that similar conditions may be common around ice giant planets throughout the galaxy. The chemical composition of these potential ocean worlds provides additional support for their habitability. The moons of both Uranus and Neptune are composed primarily of water ice mixed with rocky materials and organic compounds, creating environments that contain all the basic ingredients necessary for life as we understand it. The presence of ammonia in these systems acts as a natural antifreeze, allowing liquid water to exist at temperatures as low as 100 degrees Celsius, while the rocky components provide sources of essential elements such as phosphorus, sulfur, and various metals that are required for biological processes. The energy sources available to drive biological processes in these hidden ocean worlds extend beyond simple chemical energy to include the complex radiation environments created by the chaotic magnetic fields of the ice giants. The charged particles trapped within these magnetospheres could provide energy for radiolysis, the breakdown of water molecules by radiation to produce hydrogen and oxygen, creating chemical gradients that could be exploited by chemosynthetic organisms similar to those found around hydrothermal vents in Earth's deep oceans. The combination of chemical energy from radiolysis, thermal energy from tidal heating, and the continuous supply of organic materials through geological processes could create energy-rich environments capable of supporting complex ecosystems. The discovery of potentially habitable conditions within the ice giant moon systems has sparked renewed interest in future exploration missions to these distant worlds. However, the extreme distances involved create enormous challenges for spacecraft design and mission planning. Any mission to study these moons in detail would require decades of travel time and would need to operate autonomously in the harsh radiation environments and extreme cold of the outer solar system. Advanced propulsion systems, such as nuclear-powered spacecraft or solar sails, may be necessary to reach these worlds within reasonable timeframes and conduct the detailed studies necessary to determine whether they actually harbor life. The potential for life in the outer solar system also has profound implications for understanding the possibility of life around other stars. Recent exoplanet discoveries have revealed that ice giant type planets may be among the most common types of worlds in the galaxy, suggesting that moon systems similar to those around Uranus and Neptune may exist around countless other stars. If life can exist in the subsurface oceans of these distant moons, it would mean that the universe contains a vast number of potential habitats for life, far exceeding the number of planets that orbit within the traditional habitable zones of their stars. The legacy of Voyager 2's discoveries at Triton and the ice giant systems continues to influence our understanding of where life might exist in the universe. The revelation that active geology and potentially habitable conditions can persist in the extreme cold and isolation of the outer solar system has expanded our definition of habitable environments and demonstrated that life may be possible in places we never previously considered. These frozen worlds, existing in perpetual darkness billions of kilometers from the sun, may harbor some of the most extensive and diverse ecosystems in our solar system, hidden beneath their icy surfaces in vast oceans that have remained liquid for billions of years. As we continue to study these distant worlds and plan future missions to explore them, we may discover that the most significant discoveries about life in the universe await us not on warm, Earth-like planets, but in the hidden ocean worlds that exist throughout the cold, dark reaches of space. The technical achievement represented by Voyager 2's successful encounters with Uranus and Neptune stands as one of the most remarkable feats of engineering and navigation in human history, requiring the spacecraft to operate flawlessly for over 12 years while traveling more than 4 billion kilometers through the harsh environment of deep space. When Voyager 2 was launched on August 20th, 1977, it was originally designed for a 4-year mission to study Jupiter and Saturn. But through careful planning, precise navigation, and the fortunate occurrence of a rare planetary alignment that happens only once every 175 years, mission engineers were able to extend the spacecraft's journey to include encounters with both ice giants, transforming a regional exploration mission into humanity's first and still only grand tour of the outer solar system. The spacecraft's ability to maintain precise navigation and continue functioning far beyond its design specifications while operating in conditions for which it was never originally intended represents a triumph of human engineering that enabled discoveries that continue to reshape our understanding of planetary science today. The challenges facing Voyager 2 during its extended mission to the ice giants were unlike anything encountered by previous spacecraft, beginning with the fundamental problem of operating in an environment where solar energy becomes virtually useless for power generation. At the distance of Uranus, sunlight is 400 times weaker than at Earth, and by the time the spacecraft reached Neptune, solar energy was nearly 900 times dimmer than the energy available to spacecraft operating in Earth orbit. This meant that Voyager 2 had to rely entirely on its 3 radioisotope thermoelectric generators, which convert heat from the radioactive decay of plutonium-238 into electricity, providing a steady but continuously declining power source that decreased by approximately 7 watts per year throughout the mission. By the time of the Neptune encounter, the spacecraft was operating on only 420 watts of electrical power, less than a typical household microwave oven. Yet it had to maintain all vital systems while simultaneously operating cameras, spectrometers, magnetometers, and radio transmitters to conduct scientific observations and communicate with Earth. The navigation challenges for reaching Uranus and Neptune required unprecedented precision in spacecraft trajectory planning and execution, as the tiny gravitational influences of distant planets and the accumulated effects of small measurement errors could cause the spacecraft to miss its targets by millions of kilometers. Mission navigators had to account for the gravitational effects of all major planets in the solar system, the pressure of solar radiation on the spacecraft's surfaces, the small but measurable effects of relativity on the spacecraft's motion, and even the recoil forces created by the spacecraft's own radio transmissions and occasional thruster firings to maintain attitude control. The precision required for these navigational calculations was so extreme that engineers had to develop new mathematical techniques and computer modeling systems to track the spacecraft's position and predict its future trajectory with sufficient accuracy to conduct successful planetary flybys. Perhaps most remarkably, the communication challenges during Voyager 2's ice giant encounters required the spacecraft to operate with complete autonomy during the critical flyby periods, as radio signals took over 2.5 hours to travel from Earth to Uranus and more than 4 hours to reach Neptune. This communication delay meant that any malfunction or unexpected situation during the crucial flyby periods would be discovered by mission control only hours after it occurred, and any corrective commands would take additional hours to reach the spacecraft, by which time the brief encounter opportunity would be long over. To overcome this challenge, mission engineers had to pre-program the spacecraft with detailed command sequences that would execute automatically during the flybys, essentially creating an autonomous robotic explorer capable of making split-second decisions about which observations to prioritize and how to respond to unexpected situations without any guidance from Earth. The design modifications required to enable Voyager 2's extended mission to the ice giants pushed the spacecraft systems far beyond their original specifications and required creative engineering solutions to problems that had never been anticipated during the spacecraft's development. The spacecraft's attitude control system, originally designed to point cameras and instruments at targets relatively close to the Sun, had to be reprogrammed to function in the extreme cold and dim lighting conditions of the outer solar system, where navigation by stellar references became far more challenging, and the spacecraft's thrusters had to operate in near vacuum conditions that could cause unexpected changes in their performance characteristics. The onboard computer systems, with only 4,096 words of memory and processing power less than a modern calculator, had to be reprogrammed multiple times during the mission to accommodate new scientific objectives and overcome hardware failures that developed during the long journey through space. The thermal management challenges faced by Voyager 2 during its ice giant encounters were perhaps the most severe of any spacecraft mission, as the extreme cold of the outer solar system threatened to freeze lubricants and mechanical systems, cause electronic components to malfunction, and create thermal stresses that could crack vital spacecraft structures. At the distance of Neptune, where the spacecraft received less than 1,000th of the solar heating available at Earth, maintaining proper operating temperatures for sensitive scientific instruments required careful management of the waste heat generated by the spacecraft's electrical systems and the use of radioisotope heater units to keep critical components warm. The spacecraft's cameras and spectrometers had to be specially calibrated to function in lighting conditions so dim that exposure times had to be extended far beyond their original design parameters, requiring the development of new image processing techniques to extract meaningful scientific data from photographs taken in near darkness. The data storage and transmission challenges during the ice giant encounters pushed the limits of 1970s computer and communication technology, as the spacecraft had to collect, process, and store vast amounts of scientific data while simultaneously managing the complex sequences of observations required during each brief planetary flyby. Voyager 2's digital tape recorder, with a capacity of only 536 million bits, less storage than a single low-resolution digital photograph today, had to be carefully managed to store the most important images and scientific measurements from each encounter while discarding less critical data to make room for new observations. The spacecraft's radio transmitter, operating at only 23 watts of power, had to beam this precious scientific data across billions of kilometers of space to Earth's deep space network antennas, requiring transmission times of many months to send all the collected information back to waiting scientists. The longevity of Voyager 2's systems during its extended mission represents an extraordinary testament to the quality of 1970s aerospace engineering and the conservative design philosophy that prioritized reliability over cutting-edge performance. Every critical system on the spacecraft was designed with multiple redundancies, and components were selected for their ability to operate reliably in the harsh environment of space for far longer than the original mission duration. The spacecraft's attitude control system, scientific instruments, power system, and communication equipment all continued to function nominally throughout the 12-year journey, despite operating in radiation environments, temperature extremes, and mechanical stresses that far exceeded their original design specifications. The scientific instrument calibration and data analysis challenges created by Voyager 2's extended mission required the development of entirely new techniques for extracting meaningful information from data collected under conditions never anticipated during the spacecraft's design. The cameras and spectrometers had to be recalibrated multiple times throughout the mission as their sensitivity changed due to radiation exposure and aging, while the changing lighting conditions at each planet required new approaches to image processing and spectroscopic analysis. The magnetometer and plasma science instruments had to operate in magnetic field and charged particle environments so different from those around Jupiter and Saturn that entirely new theoretical models had to be developed to interpret their measurements. The legacy of Voyager 2's engineering achievements extends far beyond the immediate scientific discoveries made during the ice giant encounters, as the mission demonstrated that robotic spacecraft could successfully conduct complex, long-duration exploration missions in the most remote regions of our solar system. The navigation techniques, communication protocols, and autonomous operation capabilities developed for Voyager 2 became the foundation for all subsequent deep space missions, while the spacecraft's ability to adapt to changing conditions and continue functioning far beyond its design lifetime established the principles of redundancy, reliability, and careful systems engineering that continue to guide spacecraft design today. The mission proved that human technology could reach and successfully study the most distant worlds in our solar system, opening the door for future missions to explore even more remote destinations and demonstrating that the boundaries of human exploration extend far beyond the limits of our own planet. Perhaps most remarkably, Voyager 2 continues to operate and return scientific data more than 47 years after its launch, having now left the solar system entirely and entered interstellar space, where it continues to make groundbreaking discoveries about the boundary between our solar system and the galaxy beyond. The spacecraft's continued operation represents an ongoing testament to human engineering ingenuity and serves as a permanent ambassador of human civilization traveling through the cosmos, carrying with it the golden record containing sounds, images, and messages from Earth intended for any extraterrestrial intelligence that might encounter the spacecraft in the distant future. Voyager 2's journey from a regional planetary mission to humanity's first interstellar probe demonstrates that the most significant achievements in space exploration often exceed the wildest dreams of their original designers, opening up possibilities for discovery and exploration that continue to inspire new generations of scientists and engineers. As we speak today, in September 2025, Voyager 2 continues its extraordinary journey through the cosmos, now traveling at a velocity of 15.4 kilometers per second relative to the Sun, positioned approximately 20.8 billion kilometers from Earth in the constellation Pavo. The spacecraft has entered a realm that no human-made object had ever explored before, interstellar space, having crossed the heliopause on November 5, 2018, becoming only the second spacecraft in history to venture beyond the protective bubble of our solar system's influence. At this immense distance, radio signals from Voyager 2 take over 19.5 hours to reach Earth, meaning that when mission controllers send a command to the spacecraft, they must wait nearly 2 full days for confirmation that their instructions were received and executed. This communication delay creates a surreal situation where Voyager 2 operates in a temporal bubble, exploring regions of space that exist nearly a full day in the past from our Earthbound perspective. The current scientific mission of Voyager 2 has evolved far beyond its original planetary exploration objectives to become humanity's first dedicated probe of the interstellar medium. The vast expanse of gas, dust, and charged particles that exists between the stars. The spacecraft's instruments are now measuring the properties of interstellar space itself, revealing the complex interactions between our solar system and the galaxy beyond, and providing unprecedented insights into the cosmic environment that surrounds our entire solar system. The data being collected by Voyager 2 is helping scientists understand how the heliosphere, the protective magnetic bubble created by our sun's solar wind, shields us from the intense radiation and charged particles that permeate interstellar space, and how this cosmic weather system affects the habitability of planets throughout our solar system. The power situation aboard Voyager 2 represents one of the most remarkable engineering achievements in the history of space exploration, as the spacecraft continues to operate nearly 48 years after its launch using the same radioisotope thermoelectric generators that have powered it throughout its epic journey. These nuclear power sources, which convert heat from the radioactive decay of plutonium-238 into electricity, are now producing only a fraction of their original power output, declining by approximately 4 watts per year as the radioactive fuel gradually decays. To extend the mission as long as possible, NASA engineers have been systematically shutting down non-essential systems and scientific instruments, making difficult choices about which capabilities to sacrifice in order to keep the most important systems operational. In March 2025, NASA made the difficult decision to power down Voyager 2's low-energy charged particle instrument, following the shutdown of the cosmic ray subsystem on Voyager 1 in February. These instruments had been operating continuously for nearly 5 decades, collecting invaluable data about the charged particle environment throughout the outer solar system and into interstellar space. But their power consumption could no longer be sustained as the spacecraft's energy budget continues to shrink. Despite these shutdowns, 3 critical scientific instruments remain operational on Voyager 2. The magnetometer, which measures magnetic fields in interstellar space. The plasma wave subsystem, which detects electromagnetic phenomena. And several other sensors that continue to provide unique insights into the cosmic environment beyond our solar system. The engineering challenges of maintaining Voyager 2's operations in 2025 extend far beyond simple power management, as the spacecraft's aging systems face the accumulated effects of nearly 5 decades in the harsh environment of deep space. The spacecraft's attitude control thrusters, which keep its antenna pointed toward Earth for communication, have been experiencing degradation that required them to fire an increasing number of pulses to maintain proper orientation, leading engineers to switch to the backup trajectory correction maneuver thrusters in July 2019, the same thrusters that were last used during the Neptune encounter in 1989. This successful resurrection of 30-year-old thruster systems demonstrates the incredible foresight and redundancy built into Voyager 2's design, as well as the skill of the engineers who continue to find creative solutions to keep the ancient spacecraft operational. The data transmission capabilities of Voyager 2 have become increasingly challenging to maintain as the spacecraft ventures deeper into interstellar space and its power supply continues to diminish. The spacecraft's 23-watt transmitter must send its precious scientific data across more than 20 billion kilometers of space to reach Earth's deep space network antennas, requiring months of continuous transmission to download even small amounts of information. The weak signal arriving at Earth carries just a fraction of a watt of power, billions of times weaker than the energy required to operate a typical household light bulb. Yet the sophisticated receiver systems of the deep space network can still detect and decode this whisper from the cosmic deep, allowing us to continue receiving regular updates from humanity's most distant explorer. Recent discoveries made by Voyager 2 in interstellar space have revealed unexpected complexity in the cosmic environment beyond our solar system, challenging our understanding of how the heliosphere interacts with the interstellar medium. The spacecraft has detected variations in the density and temperature of interstellar plasma that indicate the presence of complex structures and boundaries in what was previously thought to be a relatively uniform cosmic environment. These measurements are providing the first direct observations of the local interstellar cloud, a region of space through which our entire solar system is currently traveling, and are revealing details about its composition, temperature, and magnetic field structure that could not be determined from Earth-based observations. The magnetic field measurements made by Voyager 2 in interstellar space have provided crucial insights into the structure of the galaxy's magnetic field in our local region of the Milky Way. The spacecraft's magnetometer continues to detect organized magnetic field lines that appear to be aligned with the galactic magnetic field, suggesting that the interstellar medium in our cosmic neighborhood is influenced by large-scale magnetic structures that extend across vast regions of the galaxy. These observations are helping astronomers understand how magnetic fields shape the evolution of galaxies and influence the formation of stars and planetary systems throughout the cosmos. The plasma wave measurements being collected by Voyager 2 have revealed the presence of electromagnetic phenomena in interstellar space that generate radio emissions detectable by the spacecraft's instruments. These interstellar radio signals provide information about the density and movement of charged particles in the cosmic medium, allowing scientists to map the structure of the interstellar environment and understand how shock waves and other disturbances propagate through the space between stars. Some of these radio emissions appear to be generated by the interaction between our solar system's heliosphere and the surrounding interstellar medium, creating a cosmic boundary layer where different physical processes operate. Looking toward the future, NASA engineers estimate that Voyager 2 could continue operating with at least one scientific instrument into the 2030s, potentially extending humanity's first interstellar mission for another decade. The exact timeline will depend on the continued reliability of the spacecraft's aging systems and the careful management of its dwindling power supply, but the possibility of maintaining contact with Voyager 2 for more than 50 years after its launch represents an extraordinary achievement in space exploration longevity. Each additional year of operation provides unique scientific data from a region of space that no other human-made object has ever explored and may never explore again in our lifetimes. The cultural and philosophical significance of Voyager 2's continued operation extends far beyond its scientific contributions. As the spacecraft serves as humanity's first permanent ambassador to the cosmos, carrying the golden record with its messages, sounds, and images from Earth. As Voyager 2 continues its eternal journey through interstellar space, it will eventually pass near other star systems, potentially providing future civilizations with their first direct evidence of human existence and technological capability. The spacecraft's trajectory will carry it through the galaxy for millions of years, serving as a time capsule of human civilization that will outlast our species and potentially our planet itself. Perhaps most remarkably, Voyager 2's journey represents the fulfillment of humanity's ancient dream of reaching the stars, demonstrating that our technology and ingenuity can carry our presence beyond the boundaries of our solar system and into the vast cosmic ocean that surrounds us. The fact that this tiny spacecraft, built with 1970s technology and operated by a dedicated team of engineers and scientists, continues to function and return data from the depths of interstellar space serves as a testament to human achievement and our species' irrepressible drive to explore the unknown. As Voyager 2 continues its lonely journey through the cosmic dark, it carries with it not just scientific instruments and data, but the hopes and dreams of an entire civilization reaching out to touch the infinite. And so, we reach the end of our incredible journey to the frozen frontiers of our solar system. Having traveled alongside Voyager 2 across billions of kilometers to witness the most extreme and isolated worlds that orbit our sun. From the mind-bending distances that separate us from these ice giants to the bone-chilling temperatures that make Earth's coldest winters feel tropical, we've discovered that Uranus and Neptune exist in conditions so alien and harsh that they challenge everything we thought we knew about what constitutes a planetary environment. These worlds, sitting in perpetual darkness at the edge of our cosmic neighborhood, have revealed themselves to be far more dynamic and fascinating than anyone ever imagined. With active geology, complex magnetic fields, hidden oceans beneath frozen surfaces, and atmospheric dynamics that create some of the most violent weather in the entire solar system. The remarkable legacy of Voyager 2's encounters with these distant worlds continues to reshape our understanding of planetary science nearly 4 decades after those historic flybys, and recent discoveries about the unusual conditions during those encounters remind us that there's still so much we don't know about these mysterious ice giants. The possibility that moons like Miranda and Triton may harbor subsurface oceans and potentially habitable conditions expands our definition of where life might exist in the universe, suggesting that the cold, dark regions of countless planetary systems throughout the galaxy could contain hidden worlds teeming with possibilities we've never considered. As Voyager 2 continues its eternal journey through interstellar space, now over 20 billion kilometers from home, and still transmitting data from humanity's first probe of the space between stars, it serves as a permanent testament to our species' boundless curiosity and our ability to reach beyond the boundaries of our own world to touch the infinite. The story of these frozen giants reminds us that our solar system contains environments far more diverse and extreme than our Earth-centered perspective could ever imagine, and that the universe holds wonders that continue to surprise and amaze us with each new discovery. If you've been captivated by this journey to the edge of our solar system and want to explore more of the incredible mysteries that await us in the cosmos, make sure you're subscribed to the Lazy Cosmos with notifications turned on, because we're just getting started on our exploration of the most extreme and fascinating places in the universe. Until next time, keep looking up, and remember that somewhere out there in the cold darkness beyond Neptune, ancient worlds continue their eternal dance around our sun, harboring secrets that may hold the keys to understanding not just our own solar system, but the countless other worlds that exist throughout the vast expanse of space.